By definition, we have that the exponential function of the logarithm function is equal to set. And this is by definition, and this is always true in the real case, and of course also no in the complex case. We also have some other very known identity concerning to the exponential function, relation between the exponential function and the logarithm function in the real case. Namely that the logarithm of the exponential function in the power of set is equal to set. The question is this valid also in the complex case? And the answer to this question is no. The reason for this is the following. If we now write the logarithm of the exponential function in the power of set, then by definition, we use this definition above, we have that in this real part we should take the logarithm of the absolute value of the exponential function in the power of set, and we add this argument value multiplied with I. Okay, this is just the same as this product. And we know that the absolute value of this product must be equal to the exponential function of x, and ln of the natural logarithm of exponential function of x is just x, because this is the fact in the real case. Now turning to the imaginary part, we see that the argument value of the exponential function in the power of set, it must be just y, because set is equal to x plus iy, and the argument value of this complex number is therefore y. But we have to add 2 pi k, and adding this we obtain the following. We obtain that we arrive at x plus iy, which is set. So we have obtained this set on the right hand side. However, we get this additional term, this imaginary term, I plus 2 pi k, where k is some integer value. So this we add to the value of set, and therefore this identity is not the same in is not inherited by the real case. So since we have a multiple valued function, so we have set plus this multiple valued complex number. We are now turning to the principal logarithm of log set, which is just a unique number. It's not multiple valued, it's a single valued function, which is defined in the following way. We, instead of taking the imaginary part of the usual logarithm, we take one particular argument value, namely the principal value of set. So, and we know that the principal value of set is the angle between minus pi and pi. We could also, you know that this principal value is some branch, we call it a branch of the multiple valued argument of set. We could have used another branch, uniquely defined branch. Let me explain a little bit more in detail what I mean by this. A branch of the argument value is like this. Let's call it the principal argument value indexed alpha, for example. This value, this principal argument value is the argument between this value and this value. You see that in the principal value case, which I'm pointing to here, this alpha is just equal to 0. So we could have used other branches, and this is necessary in many important applications of the logarithm function. We don't go into the details here now, and we are not going to discuss this so much here, the application part of it, but we want to mention that we could use an other branch of the logarithm of the argument value, and therefore thereby using some other branch of the the argument value, we have some alternative definition of the logarithm, which is associated to the principal argument value, namely this, which is a uniquely defined logarithm function indexed alpha, which is just it has the same real part as above, ln of absolute value of z, but we have the imaginary part of it equal to some other branch of the argument of z indexed alpha. So this is uniquely defined. We just have to make sure that this value is between this value and this value, so it's uniquely defined. Another property that we should mention about the logarithm function is that it is always equal to the principal logarithm function of z plus I 2 pi k, where k is some integer value. Here we can use some branch of the logarithm function as well. Okay, this what I've mentioned now may for some of you be a little bit difficult, but you should not give up. Here are some tasks which are much easier to understand. Find the logarithm of 1 and the logarithm of -1. These, for example, is impossible in the real case. So this may seem a little bit odd for you, but it's possible to calculate the logarithm of any complex number in the complex case. Okay, and we also want to find the principal values of these logarithms. What we are doing in any case is to replace the number we are taking the logarithm of with some polar form of it. So in this case 1 is equal to 1 times the exponential function of I multiplied with 0. So using the general formula for the logarithm, we have that the logarithm of 1 is equal to ln of 1 plus I multiplied with the argument of 1. And the argument of 1, we know it is this angle here, plus of course some integer of 2 pi. So since the ln of 1 is equal to 0, we know that ln of 1 is 2k pi multiplied with I. If we want to consider the principal value of the logarithm of 1, we just replace this argument with the principal argument of 1, which is of course 0, because the argument of the principal argument should be between pi, minus pi and pi, and 0 is between these two values. Okay, let's turn to finding the logarithm of logarithms of minus 1. Minus 1 can be written in polar form like this. 1 is the absolute value of minus 1, and we take the exponential function of I pi. So using the formula for the logarithm, we have that the real part is ln of minus 1, and absolute value of minus 1, which is 1, and ln of this is 0, and the argument of minus pi is of course minus 1 is of course pi plus some integer of 2 pi, integer multiple of the 2 pi. So in this case we find that the logarithm is equal to this. The principal argument, the principal value of the argument of ln is now I pi, because pi is the principal argument of minus 1 according to this polar form.